The story of the Haber-Bosch process is all about, problem solving and these big scientific breakthroughs.
And it all starts with finding the right catalyst.
Yeah, right? Initially, BASF, they were using osmium and uranium based on Haber's original work.
Yeah.
But, those kind of proved to be a dead end.
Yeah, I can imagine.
Too expensive, way too scarce, and, there's the whole radioactivity issue with uranium.
Yeah, that makes sense.
Yeah.
So they had to kind of go back to the drawing board then.
Exactly. They had to revisit that earlier research on iron catalysts.
Okay.
Iron was much more available, but getting it to work efficiently was a whole other challenge.
So how did they crack the iron catalyst code?
Well, this is where Alwin Mittash and his team at BASF come in.
Okay.
They went through, literally thousands of tests.
Oh, wow.
Trying all these different, combinations.
Really?
Talk about dedication.
Yeah, I was going to say, it sounds like a monumental task.
Oh, yeah.
Did they just kind of stumble upon the right formula?
Well, there was a little bit of luck involved.
Uh-huh.
They discovered that this particular Swedish iron ore worked really, really well as a catalyst.
Mm.
And it turned out that it already had, natural promoters in it, like potassium and aluminum.
Ah, so nature kind of lent a helping hand.
Yeah, you could say that.
But did they actually understand, why this iron catalyst worked so well?
Well, believe it or not, the actual mechanism of how it worked remained a mystery for decades.
Really?
Yeah, they knew it worked, but they didn't know how. It was this black box.
Wow.
It wasn't until the 1970s that a scientist named Gerhard Ertl, he was using all this cutting-edge surface science techniques, finally unlocked the secrets of the iron catalyst.
Hold on, so they were mass-producing ammonia, but they didn't even really fully understand how the catalyst worked?
Yeah.
That's kind of unnerving, isn't it?
Well, it might seem that way, but sometimes you just have to trust the data.
Right.
And, refine that process based on what you observe.
Yeah.
Deeper understanding can lead to, further optimizations, and that's exactly what Ertl's work enabled.
Okay, so what did Ertl figure out?
So he discovered that the arrangement of iron atoms on the catalyst surface was, super important.
Okay.
There's a specific arrangement that we call the iron 111 plane.
Right.
And it creates these tiny spaces, just the right size for nitrogen molecules to fit in perfectly.
Mm-hmm.
And these spaces, along with the promoters, they all work together to help break apart the strong nitrogen bonds.
Interesting.
Which is essential for ammonia synthesis.
So it's all about creating the perfect little spot for the nitrogen molecule to split apart.
It's a little more nuanced than that, but yeah, that's the basic idea. The arrangement of the atoms and the presence of those promoters all work together to make the nitrogen more reactive.
Fascinating. So they had their catalyst sorted out.
Right.
But I imagine creating ammonia on an industrial scale involves, a lot more than just mixing the right ingredients together.
Absolutely. Producing ammonia requires a very specific ratio of hydrogen to nitrogen, 3 parts hydrogen to 1 part nitrogen.
Okay, so where did they get all this hydrogen and nitrogen from, and how do they make sure that they had that right proportion?
Well, that's where things get really ingenious.
Okay.
They combine steam reforming and air reforming.
Yep.
Natural gas and coal were, readily available.
Yeah.
And through a series of these controlled reactions, they could produce a gas mixture that had the perfect hydrogen-nitrogen ratio.
Oh, wow. So they basically figured out how to get, the exact building blocks they needed from just readily available resources.
Yeah, exactly. It really shows, their resourcefulness and their understanding of these chemical processes.
Yeah, for sure.
But figuring out the gas ratios was only one part of the puzzle,
Right.
They also needed to design a system that could handle the extreme conditions of this reaction.
I bet high pressure comes into play here. Did you mention something about explosions earlier?
Yeah.
You're right. Scaling up this process meant dealing with incredibly high pressure, something that was unheard of in chemistry at the time.
Oh, wow.
And Carl Bosch, the metallurgist who was tasked with this challenge,
You're right.
he ran into a major roadblock.
What was that?
His reactors kept blowing up.
Exploding reactors, that's a pretty serious setback.
Oh, yeah.
What was causing them to fail?
It turned out that the culprit was hydrogen.
Oh, okay.
Under the immense pressure of this reaction, the hydrogen was actually reacting with the carbon in the steel reactors.
Oh, wow.
And it was forming methane.
So the reactor itself was part of the problem.
Yeah, exactly. The methane buildup was causing cracks in the reactor walls, and that would eventually lead to these, catastrophic failures.
Yeah. It's a classic case of, needing to understand the intricacies of material science under these extreme conditions.
Right. So how did Bosch solve this problem? Did he just find like a new material that could withstand the hydrogen attack?
He considered that, but developing new materials is time-consuming and expensive.
Yeah.
And Bosch, he needed a more immediate solution.
So what did he come up with?
Well, he came up with a pretty ingenious one. He modified the reactor design itself.
Okay. I'm intrigued. What did he do?
So instead of using just a single layer of steel, he added a soft steel liner inside the strong steel jacket of the reactor.
Uh-huh.
The soft steel had less carbon, so it was less susceptible to that hydrogen attack.
So basically he created like a sacrificial layer,
Yeah, you could say that.
a clever way to kind of redirect the problem.
Any hydrogen that diffused through the liner, it could escape harmlessly through these holes that were drilled in the outer jacket. It was a brilliant solution because it allowed them to still use these readily available materials, but also ensured the safety and the integrity of the reactor.
That's amazing. Bosch really had to think outside the box to overcome that hurdle.
He did.
But I imagine there were more challenges to come, right?
Oh, yeah, absolutely. Scaling up a process like this is like conducting a symphony. You need every single part to work in harmony to achieve that desired result.
And BASF was determined to create a masterpiece.
They certainly were.
Okay.
Let's dive into how they fine-tuned their process in the next part.
Sounds good. Okay, so back to our deep dive into the Haber-Bosch process.
Right.
We've got the catalyst sorted,
Yeah.
the gas ratios are figured out, and Bosch ingeniously solved that exploding reactor problem.
Yep.
What's next in this epic saga of ammonia production?
Well, think about it this way. They've got all the ingredients. They have the oven, so to speak. But now they have to perfect the baking process,
Right.
Scaling up any chemical reaction brings its own challenges.
I bet what kind of hurdles did BASF have to overcome in, optimizing this whole process?
Sure. One key challenge was managing all the heat generated by the reaction itself. Remember the ammonia synthesis reaction? It's exothermic.
Uh-huh.
So it releases heat as it goes.
Right. So too much heat and you could damage the catalyst or even lead to, one of those energetic events we talked about earlier.
Yeah, exactly. And controlling temperature on an industrial scale is not easy.
No, I can imagine.
But BASF, they had a trick up their sleeve.
What was that?
They drew inspiration from one of their earlier successes, the sulfuric acid contact process.
So they kind of borrowed from their own playbook?
Exactly. They designed this sophisticated converter.
Okay.
Essentially, it's this high-tech heat exchanger, and it was built to manage all the heat generated by that ammonia reaction.
Uh-huh.
So this converter made sure that all the heat was removed evenly.
Okay.
So you prevented those dangerous hotspots. It's a really beautiful example of applying knowledge from one field to solve a problem in a totally different one.
Yeah, that's great.
This cross-pollination of ideas is essential for innovation.
Yeah, that's a good point. It's amazing how BASF just kept finding ways to kind of push the boundaries.
Yeah.
But I imagine,
Yeah.
all this complex engineering must have required a very high degree of monitoring and control.
Absolutely. BASF was actually a pioneer in developing all these online monitoring instruments.
Really?
Yeah, so they could track that reaction in real time.
Mm-hmm.
And it ensured that the temperature, pressure, and gas ratios were all, within that desired range.
Wow. So they were ahead of their time in terms of process control.
They had to be. To manage such a large-scale, high-pressure chemical reaction, you need constant vigilance.
Right.
And remember, they were doing all of this over 100 years ago.
It's really mind-boggling to think about, the level of ingenuity and engineering that went into this process.
Yeah.
Why should we even care about the Haber-Bosch process?
We need nitrogen in a fixed form like ammonia to be able to build the proteins essential for life.
Right.
And before Haber-Bosch, the main source of fixed nitrogen was from these natural deposits like guano,
Uh-huh.
but those were being depleted rapidly.
So without a reliable source of fixed nitrogen, what would have happened?
Well, most likely global famine.
Wow.
The world population was growing and traditional agriculture just couldn't keep up with the demand for food.
Yeah.
But the Haber-Bosch process provided a way to produce ammonia on a massive scale using readily available resources like air and natural gas.
So it's not an exaggeration to say that the Haber-Bosch process saved the world from starvation.
It's definitely one of the most significant technological achievements of the 20th century.
I can believe that.
It's estimated that more than half the nitrogen atoms in your body right now, they came from the Haber-Bosch process.
Wow. That's incredible.
Yeah.
But I'm guessing ammonia has other uses besides just fertilizer?
Oh, yeah. Absolutely. It's a really versatile chemical.
Okay.
It's used in everything from explosives to pharmaceuticals to cleaning products.
Right.
But its main impact has definitely been on agriculture. The abundance of affordable nitrogen fertilizer, that's all thanks to Haber-Bosch.
Right.
It's allowed farmers to dramatically increase their crop yields and feed billions of people.
So more food for a growing population, that's a good thing.
Oh, absolutely. There's no denying the positive
Yeah.
impact.
Yeah.
But like any powerful technology, there are downsides.
Okay, what are those?
The widespread use of nitrogen fertilizers has led to some environmental problems like nutrient runoff, which pollutes waterways and, creates those dead zones in the ocean.
Ah, the law of unintended consequences, huh?
Yeah,
A solution to one problem can create new challenges.
exactly. And it really highlights the need for a more holistic approach to technology development.
Yeah.
We can't just focus on those immediate benefits. We have to consider those long-term environmental and social impacts as well.
So to wrap up our deep dive into the Haber-Bosch process, I think the main takeaway is that it's a story of innovation, impact, and responsibility.
Yeah, it reminds us that we have the power to really shape the world with our inventions.